conductors, you know, uh, we know that metals are good conductors of electricity, but then, of course, some metals do that, job better and are mostly used for commercial production. So, but then generally, metals are malleable. It can be bent to form different shapes, either by being hit with a hammer, on an anvil, and then of course, since they can be bent to form different shapes, they can also be stretched to to such a way that they could form wires. Okay, okay. So that there you go. That's the explanation for why malleability and ductility are both possible. The regular arrangements of ions in layers makes it possible for them to slide over each other easily when a force is applied without breaking metallic bonds. Without breaking metallic bonds. Okay, so that's just a pictorial um, um, representation of the of those uh, of the crystal structure of metals, and you can see them sliding over each other gracefully, you know, in that picture. Okay, of course, this is another popular one. They are good conductors of heat and electricity. Please take note, these are physical properties. We've not come to the chemical properties.
Mm-hmm.
We've not come to the physical properties of metals. Okay. um, to the chemical properties, while on the physical properties. So the physical properties of metals. Next physical property is the fact that they are good conductors of electricity. They are good conductors of electricity, heat and electricity. Okay, so um, just need to relocate. Just give me a minute. All right, can you still hear me?
Mm-hmm.
Okay, good. All right. So they just restored our power. So next to start so okay. 1 minute, please. Okay, you can still see my screen, right?
Mm-hmm.
Okay, good. All right. So I was on about the physical properties of metals, and we were on this one that had to do with being good conductors of heat and electricity. I think this one is easy to explain. Um, when you heat a metal, uh, of course, the atoms or ions that are the closest to the source of heat will receive the heat energy and start vibrating. Okay, so their energy level will go up, start vibrating, and then what happens? They touch the next um what do you call it? The next one, and transfer that energy to the um the ions that are there. And so that keeps going on and on and on and on. And uh thanks to the mobile electrons that help to transfer the energy to the other parts of the metal, and then you know, that causes the metal to be hot in no time. Okay. Of course, some metals are better conductors of heat than others, but then largely the fact that they are good conductors of heat and electricity cannot be denied. Um, 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 okay, so that's for uh, that property. Electricity is just basically the movement of electrical charges, right, through a metal, and that is perfectly done by mobile electrons. Okay, so another property is what's that other property? High density. Okay, high density is another uh, property of metals. Density, the formula for density is mass per unit volume. Okay, mass per unit volume. So that means if you have more mass packed into a unit volume, you know, then that automatically guarantees what? A high density. And so, I mean, just look at the structure of metals, okay? Look at the structure of metals. You see that the atoms are packed together as closely as possible. So, because of that, you have high density as a property for metals. Uh, uh, you can see also the fact that there's little space between the closely packed atoms. There's no little space, you know. So that all that makes for a high density um, property of metals. Okay, so all right, so let's look at another um, uh, concept that is facilitated still by physical properties of metals. Now, we have, a mixture, a possibility of a mixture of a metal with another one. Okay, and when we have mixture, it doesn't mean that they reacted. Okay, so we need to make sure that we straighten that out. They didn't react. It's just a mixture of one metal with uh, another one. Okay. And of course, the good thing is that it can be with another metal or with a non-metal. Okay, so of course, alloys are used for different things. Most likely the aim of having an alloy is to see how you can combine the unique properties of those things that form the alloy. Did you get that?
Mm-hmm.
Okay, all right. So you can see why alloys are much stronger and harder than pure metals. Okay, so I think I've somehow explained why alloys are stronger than and harder than pure metals because of the combination. Okay, so this is really another um, reason why alloys are stronger. Different metals have different sizes of atoms. The different sizes of atoms disrupt the orderly layers of atoms and makes it more difficult for the layers to slide over each other. So whether you want to reduce ductility or you want to reduce malleability, somehow you can achieve it by what? Having alloys. So alloys are harder and stronger than pure metals. Okay, so let's see. Um, so these are examples of alloys, and the good thing is that some of them you know them already. Okay, so take a look at steel. Iron plus carbon. Okay, so that's Fe. The chemical representation for iron is Fe, and then the chemical representation for carbon is C. Okay, so when you
Mm-hmm.
have an alloy of iron and carbon, what's it called? Steel. Okay, then you now have a more refined steel, which is called stainless steel. which is formed by iron, carbon, a little bit of nickel and chromium. Okay, nickel and chromium are what they call them, transition elements. Okay, those ones are in a world or in a class of their own as metals, transition metals. Okay, then another popular alloy that we know is copper and zinc. Have you noticed that sometimes um, you have what do you call it? You can see that those coins in the picture there. Did you notice that they could depending on how they are polished, they could almost look like gold. Did you
Mm.
notice that?
Yeah.
So that's why brass somehow gives this um, um, look. Okay, but of course, those that who know how to identify real gold can still tell the difference between gold and brass. Okay, but when you combine copper and zinc, then you have that alloy called brass, and you can see it's used for making uh, coins, um, as we see in that picture. Okay. Equally, those cables there, their pins are made of brass. Okay, so you can tell that from the look in between. So take note, it's just the pins, but most likely the black part of the wire, the cable itself, is hiding or covering rather, is covering copper. Okay, so just understand that when we want to achieve some form of solidness or some form of stronger feel, we combine copper with zinc. But then when we just want it as something that can be the wire for our cable, we leave it as what? Copper. Okay, we don't need to combine it with anything. Okay, so let's see a kind of recap. Uh, Metals have the following properties: high densities, melting points, and they are malleable and ductile. They conduct electricity and heat.
Mm.
Okay, so do you have any questions so far?
No, no, no.
Okay, all right. So somehow we're somehow looking at the concepts that you mentioned that um, all covered there.
Wait, do we have to do the
Okay.
questions?
You said
Wait, do we have to do the question? Those questions.
which one? These ones?
Yeah, yeah,
Okay. Well, okay. You list five physical properties of metals, the ones we've looked at today?
yeah.
Okay, go ahead.
Solid, malleable,
Yes.
good conductor of heat, and good conductor of
Okay.
electricity.
Of electricity. Okay. Okay. The
The
malleable. All
the
right.
alloy
Okay.
is the alloy is B. Wait, is it B?
Okay. Okay. I would go with A. Remember, an
Mm.
alloy is a combination.
Oh, my bad. Because I see the big
Yes.
atoms and the small ones.
Yes. Yes. So those big atoms show that there's a different um element involved. Okay. So always remember an alloy is a mixture of what? A metal and either a non-metal or a metal and another metal. Okay. So yeah. Okay. So yeah, we can move on now. Okay, so do you have an idea of what the reactivity series is?
Um.
But I think we can
Oh.
pass. We
Is
can,
it like starting from the most reactive
yes, to the least
thing to the
reactive.
least reactive? Yeah, I know
Yes,
what it
yes.
is.
Okay, okay, that's good. All right, no problem. I think we can skip it. I'm not sure that's not highlighted in your what do you call it, for your test. So maybe we'll skip it. But if there's any of those properties that somehow silently refers to it, yes, I think I would come back to it. But since it's not what do you call it? Um, um, really directly mentioned there, I think I will just skip it. So let me just go for the ones that so that we can focus on um okay, I'm trying to okay, good, yes. This is the next one. Chemical properties of metals. Chemical properties of metals. So you notice, I think what you just have here is metal properties. So we've just basically considered the what physical properties. Now we're looking at the chemical properties. Okay, so let me go back to our slides. Sorry, let me go back to our slides. I need this thing to move. Okay, good. All right. So, chemical properties of metals. Now, um, let's look at chemical properties. Now, remember when we looked at physical properties versus chemical properties back then, if you remember, we said something that um, things that have that concept of physical changes versus chemical changes. We mentioned that physical changes are changes that could be reversed. Did you remember that class we had?
Mm, no.
Physical changes are changes that can be reversed. For instance, when you let me just give an instance. You dissolve salt in water, right? It
Mm,
becomes salt, so a salt solution, right? That is a physical change, turning the salt, which was like in a powdered form, into a liquid form and still maintaining its taste, having that salty taste. Okay. Now it's a physical change. Why? Because it can be reversed. Okay. Consider the fact that if you heat that salt solution well, what will happen? Can you tell me what will happen?
um,
What will happen if you heat that a solution that's containing salt and water? If you heat it, what will happen?
will it react with the heat?
It will do what?
Will it react with the heat? Like, would it like create like bubbles or like steam?
Okay. Yes, it will create bubbles, but then what would happen in the long run?
Will it be? It won't be reversible.
Yes.
It
So
won't.
what will
Yeah.
happen is that essentially the water would dry up. Okay, would boil and leave the salt inside the container, and in other words, it will become vapor or steam, and that way the water will do what? Will be easily separated from what? The salt. Okay. And that's what makes it reversible. Did you get that?
Mm-hmm.
So at the end of the day, you can still get back your salt out of a salt solution. So that's why we said it's reversible. And you can get back the water, in that sense. Okay. But then there are some cases where when water combines with something, that's that combination cannot be reversed. And we're going to see some now. That's the ones that you would say fall under chemical changes, which um, allude to this concept of chemical properties of metals. So let's look at some chemical properties which show that they cannot be what? Reversed. So at the back of your mind, have it that these things cannot be reversed. Once they happen. Okay. All right. So first things first. we need to remember that there are some metals that can react vigorously, and those metals are said to be reactive metals. Example is sodium. You see why how sodium reacts with water, especially. In some cases, it's even said that they explode. Okay, sometimes you don't even need to bring water close to it. It reacts with water vapor in the air. You don't need to even bring liquid water. The water vapor in the air is enough for it to do what? React. Okay. So, of course, there are also metals that are not unreactive metals. They do not react vigorously. Okay. So let's see um, um, some examples of reactions with water. So, some metals react vigorously with cold water or steam. Okay, so those ones are the reactive metals. So just remember that. And when a metal does react with water, products formed are a metal hydroxide and hydrogen. Now, I usually like to show the what do you call it? Um, what do you call it? The way the reaction will look, in a chemical format. But I'm not sure we can look at it here because these things are hiding behind uh, like a rectangle. But anyway, let's go with what we know, right? If potassium, for instance, is very reactive and it reacts violently with water, what will it form? Potassium hydroxide and what? Hydrogen. Simple. Just remember that. Okay. Potassium hydroxide and hydrogen. Now, hydroxide is usually characterized by an OH. So if you look at water, water has H2O. Can you see it?
Mm-hmm.
Good. Now, if you remember that potassium is just K, okay? So by the time on the right-hand side of that arrow, what are we expecting to see? KOH. In other words, that is what? Potassium hydroxide. Okay. Now, one of the H is still left. Okay. And that H will combine with another H to form hydrogen, H2, hydrogen gas. Okay. So remember that whenever you can
Mm-hmm.
even see from that, if you look at that picture carefully, that is a slice of potassium reacting with water. You can see something that looks like smoke there. Okay. It's not what do you call it? It's actually a gas. And if you test that gas for what it is, you will find that it is what? Hydrogen. Did you get that?
Mm-hmm.
Okay. All right, so let's just remember that. Please don't forget metal hydroxide and hydrogen. Okay, hydroxide is OH. Okay, the metal hydroxide will be the metal followed by OH, and then hydrogen is just what? H2. Okay, so and you see the good thing is that all these reactions can be explained. You don't need to start, you know, cracking your head over, how what really is formed and all that. And the good enough. Yeah, you don't have exceptions really like that, except for the ones that are unreactive, which can even be prompted. Those ones that are unreactive. Remember the reactivity series. Those ones that are unreactive, you can use a catalyst and prompt them to do what the reactive ones have just done. Okay. Different catalysts can be how do you call it, used. So that's it for reactions with water. This is another example. Calcium readily reacts with cold water to form calcium hydroxide and hydrogen gas. You can see what I said back there. Okay. Now, can you see I don't know if they usually expose you guys to these chemical formulas? Do they expose you guys to chemical formulas in class?
Okay.
Do they?
They do, yeah.
Okay, good. All right. So I hope it's possible for you to see the reason why potassium hydroxide is just KOH. There's nothing like OH2 on it. Like unlike this case, you can take a look at this one. You have calcium. Calcium has OH in brackets, okay? Those parentheses are there. And then you have a little 2, subscript 2 at the right-hand side, bottom right, okay? To show that you need 2 hydroxide ions to combine with 1 calcium ion, positive ion. Okay, so because why is it so? Because calcium is has an oxidation number of +2. Okay, now the reason why potassium doesn't need OH2 is simply because potassium has an oxidation number of +1. Okay, so it's just simple mathematics to understand that +1 can only be balanced by what? -1, which is one OH. OH has -1 on it. So just remember that +1 can be balanced by what? -1. While +2, like in this case for calcium, can be balanced by what? -2, which can only be formed by what? OH in a parenthesis with a small subscript of 2 on it. Now, also take note of the fact that you have the word aqueous, AQ, in brackets, okay? And aqueous just simply means it's in a liquid form,
Mm-hmm.
it's soluble in water, okay? So, of course, don't forget your hydrogen is sitting there. And please take note, hydrogen never sits as one atom alone. It always forms a molecule with a second atom. So that's why you always have H2. All right. And guess what? It's a gas. Okay. It's not a liquid, it's a gas. All right. So that's why you have the G there. Okay. So let's move on. Um, that's a picture there showing you how the reaction happened. Pieces of calcium there in a funnel that's upturned, okay, and then the water, they react in the water, okay, and those bubbles that are forming there are the hydrogen that are coming out, bubbles, and then before you know it, you see that space there, that space above there will keep on increasing. This space, I'm pointing to it now with
Mm-hmm.
annotation, the red annotation. That space will keep on increasing until all the calcium is used up. At the end of the day, this calcium at the bottom here of the funnel will be used up by the reaction. As soon as it's done, all the hydrogen will be formed. Now, please take note, I did not say all the water will be used up. Did you notice that I didn't say that? I didn't say the water will be used up because if you can see, the water is way more than the calcium, isn't it? Did
Yeah.
you notice that? Good. All right. So the water is way more than the calcium. All right. So just thought I should add and explain that aspect of this reaction. Okay. So let's move on to another uh, concept. Okay. These are more metals that uh, are reacting with water. Magnesium. Okay, magnesium would react with steam. Okay, so you can see there are some that will react with water, some will react with steam. For instance, look at potassium reacts with water. Okay, calcium reacts with cold water. So, in other words, the water doesn't need to even be heated. Calcium will do what? React with it. But now look at magnesium that is somewhat lower than, it's in the same um, group as calcium, but it's lower it's on the next row of groups of or the next row on the periodic table. So what do you notice? It needs steam to react. Okay, so But then guess what? The product is the same. Magnesium oxide and what? Hydrogen gas. Okay, I hope you can see that. Hello, Mason, are
Yeah.
you there? Okay, good. All right. Okay, let's go on. The next property we want to examine is what? Reaction with dilute hydrochloric acid, HCl. HCl, dilute hydrochloric acid. Okay, so somehow we still have hydrogen getting produced somewhere uh, um, in the mix. Okay. All right. So let's see reaction of metals with acids. Okay.
Yeah.
All right. So all right. So let's see what we have here. Uh, this is copper reacting with HCl. It says okay because it's dilute probably. So it says no reaction for copper with HCl. But then if zinc reacts with HCl, okay, so
Mm-hmm.
just understand that the zinc will combine with the Cl to become zinc chloride, okay? Zinc will combine with the Cl to become zinc chloride and leave the H to form hydrogen gas. Okay, did you get that?
Mm-hmm. Wait,
Okay.
wait, uncle. You know, like
Yes,
whenever you add water to like these equations, is it always gonna be high? Like, say for example, zinc plus water, would it be zinc hydroxide plus
hydroxide.
hydrogen plus
Yes, yes,
hydrogen? So you always have to put
yes,
the plus
please.
hydrogen.
Yes, please. Okay. It will it will create hydrogen gas. Okay. So are you good with that?
Mm-hmm.
Okay. All right. So um these are the this is like a table that shows um how the different metals react with cold water. Some react with steam, how they react with steam, and what they produce. Okay, so potassium with water will give you potassium hydroxide and hydrogen gas. Sodium with water will do what? You can see is vigorous with cold water. With steam, guess what? It will be explosive. I want you to just imagine that adding a bit of heat to the mix would make it more reactive than it normally is. Okay, so just remember that a lot of heat is produced in the process, but then at the end of the day, hydrogen will do what? Be produced. Okay, and then remember that hydrogen is what do you call it? Um, Inflammable, yeah. So you know those hydrogen balloons that you know that were created in the middle times when they were creating balloons that could float. Okay, so they were built on the basis that hydrogen is easily combustible, right? So because it's easily combustible, it equally can expand and fill up um the balloon and make it to stay on in the air for long distances. But then it was equally dangerous because of this inflammability of hydrogen. Okay, all right. Do you have any questions?
No.
Okay, all right. So let's okay, so these are more properties. So I'm just moving on. Now I want you to take a very good look at this second table. Can you see that as you keep going lower, Magnesium's reaction with cold water is what? Very what? Slow. Can you see it? Magnesium is
Mm-hmm.
very slow. But guess what? When you heat it up, when you heat up the water to become steam, what happens? Its
When
reaction with steam is what? Vigorous.
vigorous,
Okay?
yeah.
Yes. All right. Now, of course, you can see the case of zinc. Zinc doesn't even react with cold water. See that? It doesn't react with cold water. Um, but then reaction with steam is moderate. Okay. And then by the time you now go to the next one, which is iron, iron doesn't react with cold water either. It reacts with steam slowly. Okay. Um, okay, so now iron now forms something slightly different. And I think that uh, difference also starts showing from um, what do you call it? Starts showing from even from magnesium. So yes, I think I now understand the question you were asking. If it always happens that way, okay. So there are some exceptions. So for instance, now look at what happens when hot magnesium burns in steam. Okay, hot magnesium and steam. When it's magnesium and just and water, what do you have? Magnesium hydroxide plus hydrogen gas. But then when it's hot magnesium, in other words, you heat up the magnesium and then you combine it with steam again. So that means both the magnesium and the water are hot, sufficiently hot. Instead of you to have magnesium hydroxide, what do you have? Magnesium oxide and what? Hydrogen. Did you see the difference?
Yeah.
Okay. So, well, one thing that you can be sure of is the fact that hydrogen will be given off. Okay. So yes, if you want to say which one, what products are you sure will is common to all of them, hydrogen, hydrogen gas will be given off.
Mm-hmm.
Okay. All right. So of course you can now see the guys that don't even react at all. They don't react with anything. They don't react with cold water. They don't react with steam. Lead, copper, and what? Silver. Okay.
Mm-hmm.
All right. Any questions?
No.
No. Okay. Okay. Now, do you know the good thing about not being able to react with cold water and with steam? It means that these metals can be used for some real life scenarios where you know, what do you call it? Some real life scenarios where no matter how the temperature is and no matter how much rain falls, these guys just don't react at all. Okay. So for instance, now look at copper. Copper is used for making wires, isn't it? High tension wires stretch over long distances, and some of them are exposed. In fact, they are usually exposed to rain all through the year. They are exposed to
Mom?
this. Did you get that?
Sorry, uncle. Yeah, pardon, mom? Yes, it is.
Okay.
Sorry, continue. Yeah, it is. Sorry, uncle.
Okay. All right. Okay. So because of that,
Yeah, yeah,
do you still want to respond to her?
yeah. Mom, yes, it is. Okay, yeah,
Can I continue now?
yeah.
Okay, good. All right. So copper doesn't have any reaction. Because of that, it's the best material to be used for wires, for making wires. Okay. Okay, so here we go with the dilute reactions of metals with dilute hydrochloric acid. So you can see there how potassium reacts with HCl. What does it form? Potassium chloride and hydrogen. Hydrogen gas is released. Same thing with sodium, sodium combining with HCl to form what? Sodium chloride. You know that sodium chloride is salt, right?
Mm-hmm.
Good. Okay. So now technically there's something we can say about metals reacting with what? Acids. They would always form what? A salt and what? Hydrogen. So if we understand that sodium chloride is a salt, nothing stops potassium chloride from being a salt. Did you get that?
Yeah.
Same thing with calcium chloride. Okay. The only thing is just that we don't know them because we don't use them in the kitchen, or we don't use them for our daily this thing the way we use sodium chloride. Okay. But guess what? That doesn't change them from being what? Salts. Okay. So sodium chloride, potassium chloride, calcium chloride, they are all what? Salts. Okay. All right. So equally notice which ones are explosive, which ones are very fast. And I guess as we go down, of course, as we go down the reactivity series, you will see that from very fast, you just have fast, moderately fast, slowly, very slowly, no reaction, no reaction. Okay. So, but the good thing about it is that there's consistency. You see the metal chloride forming and what? Hydrogen gas being released. Okay. So I hope you got that.
Mm-hmm. Wait, can you go back
Okay.
up so I can screenshot it?
Okay, yes.
So you didn't get it. Thank you.
Okay.
Yes.
All right. Okay.
Yes.
Okay. So here we go. We have key concepts that we have discussed so far. Like I said, that first one is not all the time, but most of the time, when what metal reacts with water, what do you have?
Metal hydroxide hydrogen. Plus hydrogen.
Yes, and hydrogen, good. And of course, the less reactive metals react the when heated in steam. And then sometimes when you heat the metal itself, you equally get a less reactive metal to even do what? React itself. Okay. So most metals react with what? Dilute hydrochloric acid. Please take note, it didn't say all
I'm
metals.
doing it.
Okay. It didn't say all metals. Okay. All right. So do you have any questions?
Mm,
Okay. Okay, so I think this is basically an exercise to just help us to um um okay, but I'm not sure it's complete. I'm not sure it's complete. There's something missing somewhere because there's a kind of reference to um something. Okay, but let's just look at them. I think the answers are there, so we can go away with the basic concepts that we need to remember. So why is a metal? From this information alone, it may be deduced that Y cannot exist as a gas. And I want to say, quickly add, cannot exist as a gas in what? At room temperature. Okay. Did you get that?
yeah.
Okay, so it cannot exist as a gas at room temperature. Okay, the next one says, which of the following best represents the structure of an alloy? So, can you see why
Is
D?
is is it D then?
Yes, yes, it is. It is very much D because of the difference in the shapes of the atoms. Okay, all right. So this one says aluminium is found to be very resistant to corrosion. Okay, actually, I'm not sure we have not discussed corrosion, but of course, corrosion is formed when uh, something like zinc is exposed to the atmosphere. Uh, it easily corrodes. Okay. Um, but okay, we are going to. I'll find a material on that, and we'll talk about it. Corrosion is the next thing we'll talk about. But okay, maybe let's skip this one because we've not looked at corrosion. Okay. Okay. Can you see this bit? Can you see this bit?
Yeah.
Okay. So the relative positions of metals X, Y, and Z in the activity series are indicated by the following abbreviated table. In each case, select from the metals X, Y, and Z the ones which do not react with HCl, react readily with cold water. The ones that does not react with cold water. Of course, you can see that the ones that do not react with uh, dilute hydrochloric acid are at the bottom. I mean, it's not strange at all that Z is going to meet that criteria. And the one that reacts readily with cold water is straight there at the top of the reactivity series. Okay. And then, of course, the one that's somewhat in the middle does not react with cold water, but reacts with dilute hydrochloric acid, somewhat in the middle. Okay. Um, um, okay. I think we can move on.
Okay. Wait, Uncle, you
Yeah.
see tomorrow can we have another class because the test is on Tuesday as well.
Okay. Okay. Um, Tomorrow. Okay. Let me see. I hope. Okay,
Yeah,
no
it's on
problem.
Tuesday.
Well, will
No,
we
wait,
have, is
Wednesday,
it
sorry.
Tuesday or
Sorry, Uncle, it's on
Wednesday?
Wednesday, sorry.
So if it's
Oh,
on
okay, what
Wednesday,
about Tuesday? Tuesday, Uncle. Can
hmm,
you have the class on Tuesday?
I'm trying to look at my schedule now. Um, hmm, okay. Okay. My schedule on Tuesday might be a bit busy. I hope I should be able to have that class. Okay. All right. Yeah, I think that should be workable. Okay. So Tuesday, um, at um at 6, I think should work. 6:30. So I think Tuesday would be at 6:30 if we are meeting on Tuesday.
Okay.
Okay. All right. So um okay. Okay. All right. So these are just some um some basic concepts that we have. Let me see. Okay, so you can see this is basically like a review of the ones that we've looked at. Physical properties of metals, high melting and boiling point. Um, of course, uh, I don't know, can we consider carbon? Carbon is a non-metal. Okay, so this is like contrasting a metal and a non-metal, right? High melting point and high boiling point, while carbon has low melting point and low boiling point. Metals like iron have high density, carbon has low density. Iron is a good conductor of heat and electricity, while carbon now Uh-huh. So there's a small, I think they didn't want to include electricity, but carbon is a poor conductor of heat and, well, electricity generally. Okay, then we have ductility as a property for iron and lack of ductility as a property for carbon. Metals are malleable while carbon easily breaks, okay? And if you are looking for a very good example for carbon, you can look at that black part in your pencil, okay? The the bit that makes your pencil write, okay? So that part is carbon, it's made of carbon. So you can see it easily breaks. Okay, all right. Because it can't bend easily. Okay, so these are basically like a review. Good conductor of electricity used to make electrical wires, ductile, malleable, um, and high melting point. Okay, all right. Let me see. Does this bit? Okay, this bit is just um like an infograph. Okay, so let me see if we've basically looked at what do we need to look at? Corrosion. Okay, we've looked at metals and water, right? Hello, Mason, are you there?
Yes, uncle.
Okay, we've looked at water, metals and acids, and then somewhat also looked at pure metals and alloys. Okay, so let's reserve um maybe the other bit for corrosion on Tuesday. We'll be able to cover corrosion and then maybe review the other things that we've looked at today. I think that would be okay, right?
Yeah.
Okay. All right. So let's just do that for Tuesday evening.
Okay.
All right. So um I think we can end today's class now. Um, okay. So I hope I can send a reminder on Tuesday as soon as I've started the class, and I believe you remember. Okay, so um enjoy the rest of your evening.
Okay. Thank you, uncle.
Okay, you're welcome.
Uh, good evening. Have a good evening.